The commutator of two operators a and b is a new operator given by the following expression: a hat b hat minus b hat a hat. This is commonly abbreviated using square brackets and a comma. This looks pretty abstract. Let's make it a little more concrete by applying the commutator to some function f. Bracket AB operating on f equals, if you write it out, AB minus BA operating on f, which then distributes out to ABF minus BAF. This is how the commutator works. Let's look at a simple example. Take A to be the position operator x, which is just a multiplication by x, and B the momentum operator along the x direction, px, which is equal to minus I h bar ddx. Now let's compute the two components of the commutator separately first. So x bracket px bracket equals x times minus I h bar df dx. We have applied the px operator to a function f first, and this is equal to minus I h bar x df dx. The second term, ba, equals to px hat x hat f, which is minus I h bar ddx of the product of x times f. Now here we have to apply the product rule, and we get minus I h bar times f plus x df dx. Taking the difference between these two terms of x hat px hat minus px hat x hat operating on f, we see that the term in the first expression cancels with the second term in the second expression, and we get I h bar f as a result. Now we can drop our helper function f and write finally for the commutator x hat px hat commutator equals to I h bar. The commutator is non-zero. Generally, if the commutator of two operators a and b is non-zero, we say that the operators don't commute. Otherwise, if the commutator equals to 0, we say they do commute. Clearly, in our example, the two operators x and px don't commute. This commutation relationship is actually a very fundamental one in quantum mechanics. It is called the canonical commutation relationship. Operators that commute have one very important property. They have a common set of eigenfunctions. So if a and b commute, they share the same eigenfunctions. This is easy to see. Let's assume psi is such a common eigenfunction and write down a two eigenvalue equation. So a operating on psi equals eigenvalue a times psi. B operating on psi equals eigenvalue b times psi. Now start with BA psi. According to the first eigenvalue equation, this is b operating on a times psi. Now we can pull the a constant out and we get a times b operating on psi, which according to the second eigenvalue equation is a times b times psi. We can switch the two numbers around and write b times a times psi, but now the inner part, a times psi, can be written with the help of the first eigenvalue equation. We get b times a hat operating on psi. Now we can pull the b constant into the operator and we get a hat operating on b times psi, which according to the second eigenvalue equation equals a hat b hat psi. So we see that b hat a hat psi equals a hat b hat psi. In other words, A hat B hat minus B hat A hat operating on psi, which is also written as the commutator of A and B operating on psi, equals 0. So from this clearly follows that the AB commutator equals 0. So we see that if A and B commute, they share a common set of eigenfunctions. This does not hold for the non-commuting operators. There, an eigenfunction of A is not an eigenfunction of B, and vice versa.